Today's lesson focuses on collision theory. When reactants come together to form products, there are two conditions that have to be met in order to have what we call a successful collision. So we wait and we want to have our reactant molecules collide together. And when they collide, we'll know that the collision was successful if two things happen. First, you have to have correct orientation of your reactants. And secondly, you have to have sufficient collision energy in order to start breaking your reactant bonds. So let's start to talk about orientation of reactants. And keep in mind, these are theoretical ideas that chemists have come up with. So they feel that if reactant particles collide together, they must have the proper orientation and a correct collision geometry. And when that happens, they have this correct alignment or positioning of the colliding molecules. Here's an example of 4 types of collisions that could occur between two reactants, and showing here that this is the only one right here that would have correct alignment or positioning to have a successful collision. All these other scenarios right here, here's another one right here, they are showing us two reactants that are colliding. However, the orientation or the alignment isn't proper. So what would happen here is those reactant particles would just bounce off of each other, and you wouldn't have an actual reaction happening, and you would not form products. The second condition for a successful collision is to have an appropriate amount of activation energy. So activation energy is energy that is sufficient or enough to break the bonds of our reactants and to begin to form the products. So there is a minimum amount of energy required for every single chemical reaction. And this energy is called activation energy. Okay, so this is sort of an important term right here for you to know about. Some reactions, their activation energy is rather low. And so oftentimes at room temperature, there's enough thermal energy in the room that the reaction is spontaneous and it can occur just with the amount of energy, thermal energy that is located in the room. But lots of times we need to supply extra energy for these reactions. And the amount of collision energy that we need, or activation energy, depends on the kinetic energy of the particles. So this is why oftentimes heating up our system or the surroundings, of the system helps to get the reaction to occur a little bit faster. Here is an image or a visual to show you how these reactant particles need some activation energy to get the reaction going. So here are some reactants right here. Let me get my pen going. Some reactants right here. And in order to make our products, which we see down here, the reactants need to overcome an activation energy barrier. Okay, so again, sometimes the heat of the room is enough to overcome the barrier. All of them, every single reactant combination has to overcome this barrier. And so the reactants will get this extra activation energy that is needed, and then the reactants can start to collide and break the bonds and start to form the products that are needed for that particular reaction. Because every reactant combination has to overcome activation energy, and because activation energy is dependent on the kinetic energy or the temperature of your reactant particles, we use a Maxwell-Boltzmann distribution curve to kind of highlight the amount of energy or activation energy that our substances already contain. So this graph shows the distribution of energy over some type of reactant particle. So you see here that we're plotting it towards number of particles. So here are the most amount of particles that we have right there. And what we notice is that the energy is not so great, okay? And we see here that it's a moderate amount of energy. And chemists say on average that our particles contain like a medium amount of energy. Some particles have very low amounts of energy, as we see over here. And of course, energy is increasing as we move along the graph. Down here, this would be high energy, and not a lot of particles have high energies at any given temperature. Some do, but the majority have what we call moderate or medium amounts of energy. In a typical chemical reaction, there's only a few reactant molecules that would have that high enough amount of energy down here in order to get a reaction to start occurring. The majority of molecules are under this curve here with a medium amount of energy that is not sufficient enough to reach that activation energy barrier. So what chemists try to do is they try to shift the energies of all these reactant particles to get them over the activation energy barrier. And this Maxwell-Boltzmann distribution is showing that. So we see here that we have two different temperatures. And here's T1. This is our traditional Maxwell-Boltzmann distribution curve that we see here. Here's T2, and T2 is showing us a higher temperature. We can tell this because we have less molecules at a moderate amount of energy. We have less molecules at a higher amount of energy right here. And we notice that the whole curve of the energy and molecule graph has shifted. And if this is the EA barrier right here, we notice that a whole lot more molecules now, sorry, I'm on other lines, now have that sufficient activation energy in order to keep the reaction going. Initially, it was just this little amount right here that had sufficient activation energy. So by increasing the temperature, we drastically change the kinetic energies of our molecules, and we allow them to meet that minimum activation energy barrier to start breaking bonds and creating new products. This right here is supposed to be a greater than or equal sign. And so this is what we want to do, is we want to increase the amount of kinetic energy relative to the activation energy. This is an important little stat to know over here, that a 10-degree rise in temperature approximately doubles the rate of any reaction. Okay, so temperature really has a significant effect on the reaction rates of our reactions, and it's largely to do with this activation energy barrier. We allow it to be overcome a lot easier when the overall temperature is higher. So just to recap, we need two conditions to have a successful collision. So we have to have proper orientation and sufficient collision energy. And so here's an example of where we have reactants moving too slowly. So when they actually collide, maybe they don't have enough EA to break the bonds and start making products. Maybe they also don't have the right orientation as well. Here is an example of where the reactants are not facing the right way. So we notice here by these little lines, they actually are moving pretty fast. So they've got a lot of initial kinetic energy, but they're not colliding with the proper orientation. And so they bounce off and we get no reaction. But here is a combo where we have good activation energy, we have proper alignment, and as a result, we now will start to see our new products being made and the chemical reaction proceeds. We know that all of our processes on Earth are either endothermic or exothermic. So we now have the ability to show each of these types of reactions graphically and relating them to these energies that are needed in order to have these reactions occur. So if we have an exothermic reaction, what happens here is the reactants that you start off with are at a higher potential energy. Okay, so just naturally, the combination of two reactants together collectively will have a high potential energy. And typically what will happen is they really won't need a whole lot of activation energy in order to get over this barrier and form products. When that happens, because they only use up a small amount of activation energy in order to begin to make products, they have all this extra energy available to them that they originally had stored in their bonds, and they release this now as heat to the surroundings. Okay, so we know that an exothermic reaction releases energy. And so graphically, you can actually tell. So if we had numbers assigned here, right, we would know what was the potential energy of the products once they were formed. We know what the potential energy of the reactants are. And the difference between those two represents the enthalpy of the entire reaction. Here we can see how much extra energy we need in order to create those products, so to get over the activation energy barrier. And at the top of the activation energy barrier is something called an activated complex. Sometimes it's also called a transition state. And this activated complex is like a big blob or like a mishmash of reactant molecules. So this is when the reactants are colliding and they're trying to break bonds and also collide with sufficient energy. And when that happens, they proceed on to make products. But sometimes if they don't have one of those conditions met, they form this activated complex, which is like all the reactant molecules stuck together. And it will either revert back to reactants or it will begin to make products. An endothermic reaction can also be shown in a graphical way. So the difference between endothermic and exothermic is that in an endothermic reaction, we now have to add energy into the system. And the reason that we have to do that is because our reactants have a very low potential energy. Look how far down they are initially. And again, it's just the way that they combine collectively, they have a lower potential energy. And they need a huge amount of extra energy to be added in order to create our activated complex, in order to meet this minimum activation energy that is needed. And hopefully at the top right here, we really hope there's sufficient energy, there's proper orientation, and then we can go on and we can make products. And you'll notice again that the enthalpy value is always the difference between the PE of your reactants and the PE of your products. So this difference between the two represents the enthalpy, or in this case, the energy that would be needed to create those products. So here's a little summary of the information that we can get off of these potential energy diagrams. So just looking at this one here, we can tell that this is an exothermic reaction. And I can tell that because my reactants are at a higher potential energy than my products. So they'll need some type of activation energy, obviously, to get going, but they don't need as much as an endothermic reaction does. Remember that the enthalpy, I'll just put a delta sign here, is the difference between the PE of your reactants and the PE of your products, okay? Do not measure enthalpy going up from activation energy. It does not apply. This is outside energy that is required. It is not the change in energy from reactants to products, which is what enthalpy measures. Remember also that all reactions are reversible, okay, in theory. So if we decided to reverse this reaction and go the other way, we notice that this would now be an endothermic reaction, and we would have a huge amount of activation energy to overcome in order to start to go backwards and make products on the other side.